All right, well, welcome back. I'm George Trimble. This is the next part of our celestial navigation course. Um, in our previous presentation, we utilized the spherical law of cosines in order to solve the navigational triangle. And this allowed us to actually come up with two numbers, the zenith and the intercept distance, that allowed us to move from an assumed position and draw a line of position. Now, if you're anything like me, you don't like to utilize tools that you don't understand. And it's true that you can use the spherical law of cosines without a great level of understanding of where it comes from or why it works, and you'll get the right answers. So this lecture is for those of you who want to take a peek under the hood and really understand the mathematics behind celestial navigation. And so if you are something of a mathematical masochist, as am I, this will interest you greatly. If the mathematics behind the workings of spherical trigonometry don't interest you, this will be a lecture you can skip. You really don't need this in order to do what we did last time. So, without any further ado, let's talk about the spherical law of cosines. It's used in celestial navigation to solve for two things: the co-altitude and the azimuth angles in the navigational triangle. And there it is. And let's break it down just a little bit. We're interested in finding side A, which in this case is the co-altitude. And so the formula as written gives us the cosine of that altitude. And to solve for the co-altitude, we need to take the anti-cosine of everything here on the right. So let's look at here on the right. What's there? We've got a side that we're missing and we're interested in finding as A, little a. We've got the cosine times the cosine of the other two sides. So we've got the product of the cosines of the adjacent sides of the side we're interested in finding. And we're going to add to it the product of the sines of those same adjacent sides times the cosine of the enclosed angle A. And this angle is the local hour angle. Notice that the local hour angle, big A, is opposite the same named side, little a, and that's true in geometry in general. The sides are named as the small variable of the opposite angle. And so here we have two sides, C and B, that are used as their cosines, and here they're used as their sines. C and B are the co-declination and the co-latitude from our navigational triangle. All right. Now, as I say, you can drive this car. It'll get you where you need to go, and you really don't need to understand how it works. But if you really want to know what's under the hood, what makes the equations tick, this is for you. And I warn you, this is going to be a deep dive mathematically, so be prepared. If not afraid. All right, we have to start with Euclid and plane geometry. We are going to need the planar or Euclidean law of cosines in order to make progress and discover the spherical law of cosines. I should say that triangles on a sphere are similar to triangles on a plane in that they each have three angles and three sides. That's about where the differences end. The sum of the internal angles of a triangle, always on a plane, always sum to 180 degrees. But on a sphere, there is greater than 180 degrees, and it depends on the curvature of the sphere how much in excess of 180 degrees is present. And so some of the rules that we're familiar with, like the Pythagorean theorem and etc., they don't apply to spherical triangles. We need to discover the equivalent rules in spherical trigonometry. And so the spherical law of cosines differs from the planar law of cosines. I'll show you how we can discover one from the other. We're going to begin now with the planar law of cosines. I'm going to help you derive it here. Here's a triangle. And I've labeled, just for the time being, this angle is beta and this angle is alpha. This is A and this is B for the length of the sides. And I'm going to cut this in such a way that I create a right angle here, as you see. And it creates two separate triangles, and I'll break them apart. And although the length of the entire base of this triangle is C, since we've broken it in two, I'm going to label the component parts X and Y. So now we've got two triangles with sides X and A, enclosed angle beta, and this triangle here, sides Y and B, enclosed angle alpha. And I'd like you to see that for this left-sided triangle here, the cosine of beta is the base over the hypotenuse, X over A. And so the base, by multiplying both sides of the equation by A, is A cosine beta. Okay. And we can see, using similar logic, that the cosine of angle alpha here is Y over B. Similar logic, we're finding the cosine, it's the base over the hypotenuse, and so we can solve for the length of the base as Y equals B times cosine A. Now, we recall that C, this value, the base of the original triangle is comprised of both X and Y, the sum of the two. And so we can then substitute and say that C is equal to A cosine beta, which is X, from here, plus B cosine alpha, which is Y, from here. Okay? Now, I'm going to multiply both sides by C. Why? Because I can, and because it helps us make progress in the end. So what I have here is C times C is C squared, and I'm going to distribute this C into here, into the parentheses, and what I get is C squared equals AC cosine beta plus BC cosine alpha. That's just the C multiplied in here and here over the using the distributive property. This is an important formula, and I want to remind you that the square of C is equal to these two values summed together, AC cosine beta plus BC cosine alpha. All right, that's C squared. Now on to the next slide. I've decided to name this angle here kappa because I don't want to use a capital C because it's easily confused with a lowercase c. So they have the same sound, the same k sound. So I'm naming this angle kappa, and it's related as being the opposite angle to this side little c. And now we're going to split the triangle differently. I'm going to split it this way. And we're going to do essentially the same thing. We're going to split the triangles. Now I've got two right triangles. And since B is being split, this whole side is being split into two, I'm going to name these X and Y, okay? So that the cosine of the angle kappa in this top triangle here, that's the base divided by the hypotenuse. You kind of have to turn this in your head into standard position. But it's X over A, so that A cosine kappa equals X. And likewise, when we take with this angle alpha and discover the base value, that's the cosine of alpha equals Y over C, such that C cosine alpha equals Y. And then recognizing that the value of B is X plus Y, we can substitute b equals a cosine kappa plus c cosine alpha. And again, I'm going to square both sides because I can. It's not illegal. And actually, I shouldn't say square both sides. I'm going to multiply both sides by b. I take it back. We're going to not square both sides, but we're going to multiply both sides by b because I can and because it helps make progress towards an interesting answer, a result that has value. And so this side becomes b squared. The other side, I distribute the b into the parentheses using the distributive property, and I get b squared equals ab cosine kappa plus bc cosine alpha. That's another result. Now on the previous side, I showed you that we discovered c squared. Now we've discovered b squared, and as you might guess, in this next slide, we are going to discover a squared. So this time we're going to split the triangle from the final remaining angle, and we're going to drop a perpendicular to this base A, and we're going to discover what we can about those relationships again. We split each triangle, and we find that for angle kappa, that's here, the cosine of kappa is x over b, that's the base over the hypotenuse once again, so that b cosine kappa equals x, the base. Again, we go to the other triangle and we solve for the cosine of beta, which is y over c, such that c cosine beta equals y. And we have that a equals x plus y. That's just this, has been broken into this component and that component. And so we can substitute a equals b cosine kappa from here, which is x, plus y, which is c cosine beta from here. And we get this equation here. And because I'm able to, and because I want to, I multiply both sides by a. And so we get a times a equals a times this quantity, this sum within the parentheses, and I distribute a into the parentheses, and I get a squared equals ab cosine kappa plus ac cosine beta. This result is of value to us as well. I now have a value for c squared, for b squared, and for c squared. And notice, I'm actually going to go back. I want you to notice that I've couched a squared not in terms of x and y, but in terms of a and b and the angles, right? So x and y were just placeholder names. They don't have any further need in the future. They were just placeholders to get us progress towards couching a square in terms of ab cosine kappa and ac cosine beta. All right. So now we have c squared is this, b squared is that, and a squared is this. And they were all derived using similar techniques in logic. And so they have a certain symmetrical appearance to them. They look to be similar because they came about using the same strategies. Now, I'm going to take a squared plus b squared, and I'm going to subtract c squared. Now, I can only tell you that I chose this because it works in the end. We could have fiddled around trying a squared minus b squared minus c squared, or a squared plus b squared plus c squared, but in the end, this one gave the result that was interesting to us, and it's the reason why we have a minus sign in front of the c squared. It allows certain things to cancel, as you'll soon see. So when I decide to take a squared plus b squared plus minus c squared, I substitute. Here's a squared. So a squared is ab cosine kappa plus ac cosine beta. And there it is, right there, right here. Okay? And then I add to it b squared, which is right here from above in red. And I subtract, right here's the subtraction. I'm going to subtract this value, which is c squared. Okay? Now, when I distribute this negative sign into the parentheses using the distributive property, I get this statement on the right side of the equation here, okay? And notice this becomes minus AC cosine beta, and this also becomes minus BC cosine alpha. And what we find is I've got plus AC cosine beta minus AC cosine beta. These cancel. And this is plus BC cosine alpha minus BC cosine alpha. And so I'm able to simplify. And what drops out is everything having to do with C. C, 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 okay, right here. And what I'm left with is AB cosine kappa and AB cosine kappa. That's 2AB cosine kappa. Okay, and that's equal to the original statement of a squared plus b squared minus c squared here. So here's the complete equation right here. And notice I've got a, b, and c on the left, and I've got only a and b on the right. C has disappeared from the right-hand side of the equation, and that's because of my choice to use a minus sign in front of C here. Okay. Now, I'm going to isolate C by moving a squared plus b squared to the other side, in essence subtracting a squared from both sides and b squared from both sides, which I do here. And dividing both sides by -1 converts that into this equation here, which I've circled and colored red. So what I've got is c squared equals a squared plus b squared minus 2ab cosine kappa. And kappa, by the way, is the angle opposite of C. So here we've got the law of cosines, and what it says is for a given side, okay, C, the square of that side is equal to the square of one of the adjacent sides plus the square of the other adjacent side minus 2 times the product of the sides times the angle they enclose. The angle they enclose is kappa, that's opposite. It's the angle opposite the side in question that we're trying to solve for. And so there's the equation. This is the law of cosines. It allows us to solve any triangle. It doesn't have to be a right triangle, which is very convenient. It saves us a lot of steps. It allows us to solve any planar triangle if we know 2 sides and the angle between them, okay? It allows us to find the opposite side. So here we say the missing side of a triangle is obtained from the 2 known sides and the known angle between them. That is the law of cosines right there. And it's valuable in plane trigonometry, and we'll find that it is a necessary, what we call a lemma or a stepping stone to getting to the law of cosines for the spherical triangle, which has different properties, being, of course, inscribed on the surface of a sphere. Now, let's see if we can make some progress towards the ultimate finding, which is the spherical law of cosines. That's what we really want. Now here, we have a triangle drawn on the surface of a sphere with the understanding that each of these lines is an arc that is part of a great circle, meaning it is a circle that connects A and C, but it goes through the center of the sphere at O, the origin. It's not a small circle that does not include the center of the sphere. It's a great circle. All great circles are created by planes that join 2 points on the surface of the sphere, and the plane also includes the center of the sphere. So we got this plane here that contains AC and O that creates this arc. We've got another plane that intersects the circle, like cutting an orange, but it has to go right through the middle and include these 2 points, A and B. And we've got another cut section through B and C that goes right through the orange, so to speak, or the earth, or whatever spherical body we're talking about, but it includes the center at O. So we have a spherical triangle comprised of great circle intersections. Okay. And here we're going to label the apices, or the angles at the corners, as A, B, and C, as shown here. And the opposite sides will be named as the lowercase value. So big A opposite has side A, little. Big B angle has opposite side, little b. And big C angle here has an opposite side labeled as little c. That's standard parlance in geometry, spherical geometry. And now here I want to point out we are not going to assume that this is a right spherical triangle. None of these angles, C, B, or A, is right. It's just some random triangle, which is kind of like what we did in the last slide. We developed the planar law of cosines, which allows us to learn something about a side of a triangle without having to have a right triangle as an intermediary. And we want to do the same for the spherical case to simplify our calculations. Now, you might recognize from our previous lectures that the side A is the side we try to find. It's the coaltitude, and the angle big A is the local hour angle, and this would be the sun, and over here would be the boat, and the colatitude would be the little b, and the codeclination, the little c. So you can see how this is very much analogous to the problem we discovered in the navigational triangle. And so you can see that this should be relevant. So first what we're going to do is we're going to construct AD and AE in plane ADE tangent to the sphere A. So what I want you to imagine by this statement is we're going to take a plane, like a sheet of glass, and we're going to lay it on the sphere at point A, touching only at point A, and therefore it must be perpendicular to the radius of the sphere OA, okay? And so if we were to project from the center of the Earth, from here, the origin, if we were to project using a light source out of the glass sphere of the Earth, these lines drawn on the surface would project onto the plane that touches tangent to the sphere and cast those shadows of these lines onto the sphere, or onto the plane from the spherical surface, and it would look like this. So what we've done is we've constructed AD and AE in plane ADE. These lay in a plane, they're all coplanar, and they're tangent to the sphere at A. It's as if a piece of glass were set on the sphere at point A. It has to be perpendicular to OA. That's the definition of a tangent plane to a sphere. And these angles, or I should say the angle DAE lies on that plane, and it represents the projection of AB and AC. So that AD is a projection of AB and AE is a projection of AC. And it turns out that the angle DAE is the same as the angle BAC. Okay? So let me go through this. AD in plane AOB and AE in plane AOC. Now, what that's saying is that this line, AD, is coplanar with this whole wedge here off to the side. AOB is a plane, and AOB, this plane, also extends to contain the line AD. They're coplanar. And the same may be said of this other side of the wedge, AOC, that wedge of pizza over there, if you will, that plane is in the same plane as the line AE. Our construction ensures that's the case, and I go to some pains to point it out because it's going to be important later. And we can therefore deduce that OAD, OAD being coplanar, right? and OAE, OAE are right angles because they're part of the plane tangent to the sphere at A. They have to be tangent in such a way that the radius OA is perpendicular to the plane. Okay. And as I've said before, DAE equals BAC. Those are the same angles. One angle is in a plane and the other is on the surface of the sphere, but they start at the same point and they just diverge in curvature over time, but they start with the same angle. Okay. OB, this here, may be made to extend and intersect AD, okay, at D, like this. And the same for OC. It too may be extended out into space, being coplanar with line AE. It can eventually make contact with line AE, and they form these two triangles like wings on the sides, okay? And then we'll simply create DE like this. So we've made this interesting triangle, or set of triangles, really. We've got this one here, OAD, OAD. We've got OAE, which is a triangle. And we've also got the base of this tetrahedron, which is EOD, triangle EOD. Now, let's work with this. We're going to take some of these triangles off to the side. There's the original drawing. Okay. Now, I'm going to take OAD. That's this lateral side of this figure, of this tetrahedron. We're going to take it down here. Is that a tetrahedron? No, it's not exactly. It's a pyramid. It's a pyramid. I said tetrahedron before, but it's really a pyramidal shape. Whatever the case, we're going to work with this triangle and see what we can discover about it. And we're going to work with this other triangle, which is the opposite side over here, OAE. And we're also going to work with this triangle, which is the base, ADE. Okay? Let's see what we can discover. I'm sorry, that's not the base. That's actually this fronting angle here, ADE. That's here. And here's the base, ODE. So here's one additional triangle that I failed to point out in our previous slide. But we've got these 4 triangles to work with. Now let's see what we can discover about this first triangle here. The tangent of angle C is here, okay, and I've carried it down to here, and it represents the length of this side. And as you might recall, the length of this side in nautical miles has the same value as the angle in arc minutes at the center of the Earth. We learned that from lesson 1 in studying Eratosthenes and his discovery of the circumference of the Earth. So we know this angle, C, if we know this side. And so the tangent of C, the tangent is the y dimension divided by x, or what we would call the upright side opposite over the base, the adjacent. And so it's AD over OA. Study the diagram in your head. Try to flip the triangle into standard position to see it better. But it's AD over OA, so that OA times tangent C, and OA represents a linear distance. I didn't put the little line over it. I'm going to ask you to allow me to cheat a little bit in that regard. I'm not putting little lines over every linear distance. So I'm talking about a distance, OA, the length of the line, times the tangent of C equals AD. Now I can also discover that the cosine of C is OA, the base, over the hypotenuse, OD. And I got a problem with my mouse. I need to have some sort of debouncing in there, but pardon me while I get caught back up here. I accidentally went backwards somehow. Okay. And we can also discover the secant of c by simply understanding that the secant function is the reciprocal of the cosine function. So if I flip these or take the reciprocal, I get OD over OA. Why? Because I can, and it becomes helpful here shortly, so we're going to allow it. You might wonder, why in the world would we do all this, until you see that in the end, we discover the spherical law of cosines. Now, so by manipulating both sides, multiplying both by OA, I come up with OA secant C is equal to OD. I've isolated OD from the previous equation. And that's nice because OD is a value that I'm interested in finding. And so I have discovered in the first part here, where I'm circling, that AD here, length AD is OA tangent C, so I label that in this diagram. And I've discovered that length OD, that's this, is equal to OA secant C, which I've also labeled in the diagram. All right. So that's that. Now, relating now to this other side, we can use the exact same logic here. We're going to find the tangent of angle B, and let me move me out of the way. Angle B comes from right here. That is the angle at the center, which has the same arc minute value as the length in nautical miles of this side, AC, at least when we're talking about celestial navigation and terrestrial navigation. So I got tangent of B is AE over OA. AE over OA. Okay? And this triangle, as you might recall, comes from this diagram that we developed in the previous slide, OAE. Okay? So we decided that the tangent of B is that, and we multiply both sides by OA, and we get OA tangent B equals AE. And we've discovered side AE right here, AE. All right? And then we can discover the cosine of B equal to the base over the hypotenuse. That's OA over OE. I can rearrange, or rather I should say rename. The cosine of B would then be the reciprocal of this value. So I put OE on top, OA on bottom. And I can rearrange and multiply both sides by OA so that I have OA secant B equals OE. And now these two values can be transported into the diagram so that I assign AE the value OA tangent B from here. And I assign OE the value OA secant B from here. Okay. There we go. Now that we've done that. Now we recognize that these lines here, this one and this one, from this drawing over here, AD and AE, are also the sides of a different triangle, this one here. And so I can label those there. See, I just carry OA tangent B is there, and OA tangent C is here. And I can do the same, understanding that the base here and the base here, that comes from this diagram up in the upper left-hand corner, here is that base, and this base here, they also comprise the sides of a different triangle, and that's located here. So I put OA secant B here, and OA secant C goes to here. And so I've discovered the sides of all of these triangles simultaneously, really. Now, taking these two triangles, this one and this one, to a different slide here, and we're going to use the Euclidean law of cosines. And we're going to decide that we can discover, see, we've got this situation here. We've got A, an enclosed angle. We got two sides that we know, and we want to discover this side, okay? And so we see the opportunity to use the Euclidean law of cosines. And so we know that the square of the missing side is equal to the square of one of the adjacent sides plus the square of the other adjacent side minus 2 times the product of the sides. That's AD times AE, this times this, times the cosine of the angle they enclose. That's the cosine of A. And we replace each of these lengths. AD squared becomes this, and AE squared becomes this. And so we square OA times tangent C, we square OA tangent B, and here we have 2 times AD, which is OA tangent C, times AE, which is OA tangent B, times the cosine of the enclosed angle here. Now, what I'm going to do is distribute into each of these the square. Okay, so now I've got OA square times tangent square C plus OA square tangent square B minus 2OA tangent C times OA tangent B times cosine of A. All right. And then simplifying, this recognizes that here we've got a product added to a product, subtracted, and then a subtraction, another product, and here we've got an OA in this product and an OA. That's OA squared here. This one has an OA squared, and this product here has an OA squared. So I can take OA squared out, factor it out, and what I'm left with is tangent square C plus tangent square B minus 2 tangent C tangent B cosine A. All right, I've got this right here. I know it's painful, but keep going. We're one slide away from developing the answer we seek. Now we're going to do the same thing to discover the value of DE down here in this lower triangle. And notice these two triangles share the common side DE. This triangle here and this triangle here both share the common side DE. You can see it in this upper left diagram. You see the base of the pyramid and this red side share the common side DE. All right. So using this triangle now and its values, we have a side, we have an enclosed angle, okay? And we seek to discover the value of DE. And so we have DE squared, this is the law of cosines again. Get this a little bit up out of the way. Equals, so the square of the missing side equals the square of one of the sides plus the square of the other side minus twice the product of the sides times the cosine of the enclosed angle, little a in this case. So substituting using these values here, that OD, the length of that side, is OA secant C, and OE is OA secant B, I then replace these values with their corresponding actual lengths. So OA secant C squared plus OA secant B squared minus twice OA secant C times OA secant B times the cosine of A. This remains unchanged here. All right. Removing the parentheses by distributing the square into the inside of the parentheses gives us this, much the same as previously. Convince yourself that it's true. And then we factor out, again, we find that OA square is found in each of the factors, and so we factor it out. So OA square times secant square C plus secant square B minus 2 secant C times secant B plus cosine A. Now we have two equations for the value of the length DE, or really two equations for the value of the length DE squared. And so since this is DE squared and this is DE squared, then they must equal each other. And here's how we derive the spherical law of cosines. Watch. I got to get me out of the way somewhere here. Here's that picture we started with. Now we're going to set those two values equal to each other. And the one was this and the other was this, and I set them equal to each other. Here's that second one we just solved involving the secant, and here's the first one on the previous slide we solved involving the tangents. I recognize that OA square appears on both sides of the equation, so I just cancel it. I can divide one side by OA squared and the other side by OA squared, and it disappears. And what I'm left with is what was originally in parentheses only on either side of the equation. And now I'm going to remind you of something that I didn't remember. I had to go look in the front of the textbook on trigonometry, but these are called the Pythagorean identities. The truth is that anywhere you see secant square of some angle, here I call it gamma, that's the same as saying 1 plus the tangent square of gamma. That comes right out of the textbook of trigonometry that I have. It's printed on the inside front cover, and I've written down some of the trigonometric identities in the front of my notebook where I do some of my mathematics, and it's shown here as one of the Pythagorean identities. So there it is there. It's that second one. You'll have to trust me on this and look it up yourself. Any good trigonometry textbook will prove the truth of this to you. But we're going to use it here without question. And anywhere we see secant square of gamma, some random angle, we're going to replace it with 1 plus the tangent square of gamma. And I see here the secant square of C appears and the secant square of B appears. Okay, and it's nice because it's turning it into tangent, and everything else is couched in terms of tangent over here, which is nice. So let's do the substitution. For this, we're going to substitute with 1 plus the tangent square of C, and for this, we're going to substitute with 1 plus the tangent square of B. Everything else remains the same in this equation right here. All right. So the parentheses are superfluous, so I'll remove them, and that allows us to see that tangent square of C appears on both sides, so I can subtract it from both sides. The tangent square of B appears on both sides, so I can subtract it from both sides, and it maintains the equation balance. You see how it cancels? And what I'm left with, here I add 1 plus 1 is 2, so I have 2. And then I have this product here minus this, stays the same here. And here I'm left with negative 2 times all of this. All right. Now I divide both sides by 2, and I get this. This 2 becomes a 1. This 2 becomes a 1. This negative 2 becomes a negative 1 by dividing both sides by 2. All right. Now here, basically what I did is just got rid of this 1 by saying, okay, well, negative 1 times this is just negative this, and negative 1 times all of this is just negative all of this. And so what I've got is negative of this value and negative of this value. I'm just simplifying. And now I recognize that the secant, remember from our last slide, the secant is the reciprocal of the cosine, and so the cosine in turn is the reciprocal of the secant. And so I can convert them back and forth, and I will. The secant of C becomes 1 over the cosine of C. The secant of B becomes 1 over cosine B. I'm going to leave this alone. And here I recognize that the tangent is just another name for the sine over the cosine. That's easily shown to be the case. The sine is y over the hypotenuse, and the cosine is the x over the hypotenuse. And so when you divide y over the hypotenuse divided by x over the hypotenuse cancels, and what you're left with is y over x, but y over x is the tangent. All right, so maybe I'm saying too much. Whatever the case, I replace this tangent with the sine over the cosine for its variable, and we leave cosine A alone. All right, now what am I going to do? What I do is I move everything on this side, everything, I move it over to the other side by adding it. I add it to both sides. That leaves 0 on this side of the equation here. And here is that horrendous long sum and product over here. Now, here what I've done, since this is over cosine C, and this is over cosine B, and I've got a 1, a 1. Let's see, what have I done here? I'm going to pause here to figure out what the heck I did. There we go. Try again. There we go. All right, I'm back. I don't know why that was so perplexing to me, this step. But here I've got, in this area here, what I've got is a product. And it's a product of ratios. So all I've done is taken all the tops here and put them over all the bottoms. So I have sine C on top, sine B on top, cosine A on top. And on bottom I've got cosine C, cosine B, and 1. And so I did that. I just put all the tops on top divided by all the bottoms. That's all. And I did that for each of these. So cosine A on top divided by cosine C, cosine B. Still equal to negative 1. Now, since both of these are over cosine C times cosine B, this here, and this is being subtracted and has the same denominator, I'm factoring out the denominator as 1 over cosine C times cosine B, and I'm saying that that is multiplied by what's in these parentheses. And that is what's on top here minus what's on top here. All right? And so, and then I can actually combine them by just slipping this right underneath of this. And so what I've done is neaten up this equation. So I have sine C sine B times cosine A over minus cosine A, little a, divided by cosine C times cosine B. And that's equal to negative 1. And what I can do is multiply both sides by the denominator. And then I subtract this product here from both sides, and I'm left with the negative of this on this side of the equation right here. Okay? And dividing both sides by negative 1 gives us the ultimate answer we were looking for, which is the Spherical Law of Cosines, which says that if you want to find... Now, remember, we were interested in finding a relationship between the sides C and B and the enclosed angle A, and discovering the length of this line A on a spherical triangle, and the formula looks different than planar trigonometry law of cosines. Remember the minus 2AB cosine of the enclosed angle? Well, that's gone. That doesn't look like this. What we've discovered now is the law as it applies to spherical triangles. And it turns out that the missing side A, down here, is equal to the product of the cosines of the adjacent sides plus the product of the sines of the adjacent sides times the cosine of their enclosed angle. So the rule is different. It looks different stylistically. And so this is the ultimate thing that we need right here in spherical trigonometry. And for solving the celestial or the navigational triangle, I gave this to you in our last presentation, and I said just use it and enjoy. You don't have to understand it, but now if you followed with me, and as you could see, I could barely follow myself, but if you followed with me, you do understand where it came from. And yeah, my eyes are looking like this guy right here, right about now. All right, now, in our next presentation, I'm going to show you another approach for deriving the spherical law of cosines. And that is, or I should say this. No, I'm going to show you another approach to solving the navigational triangle without resorting to the spherical law of cosines. And this is really, it works for any spherical triangle, but you have to learn 10 right triangle relationships. You have to discover those, and then you have to use those to solve the navigational triangle by dividing it into two right triangles. And it really is for the mathematical masochist. So if you're interested in learning another way to solve the navigational triangle that does not result to the use of the spherical law of cosines, tune in next time and return with me for the next part. And I think we'll conclude for now, and I'll see you next time. Thanks for sticking with me.